Have you ever walked past a modern construction site, breathed in that sharp chemical sting of green, pressure-treated lumber, and wondered how long any of it will actually last? 10 years? Maybe 20, if the termites are feeling generous. It's one of the strangest contradictions of our era. We can split atoms, map the genome, and send messages across the planet in milliseconds. Yet our fences rot, our decks splinter, and our barns crumble before a single generation has even grown old. But now, look back, far back. In the mist-covered valleys of Norway stands the Borgund Stave Church, 8 centuries old, built from ordinary timber that should have turned to dust long ago. And buried in the clay, the Oseberg ship, its oak planks still intact after 1,000 years, continues to whisper the story of a civilization that mastered wood in ways we barely understand today. How did people without factories, without polymers, without industrial preservatives create timber structures that outlive ours 10 to 1? The answer isn't magic. It isn't just old-growth wood. It is a forgotten science, an elegant, accessible synergy of natural chemistry that modern industry abandoned in its rush for convenience. Welcome to Historia Prime. Today, we uncover the Viking wood dip, a molecular triad of pine tar, linseed oil, and hardwood ash. We'll break down why modern wood fails, why ancient wood triumphs, and how anyone, yes, even you, can recreate this lost preservation system with simple tools and a fire. Let's burn some stumps. Part 1. The Modern Failure. Why your deck is doomed. To understand the genius of the ancients, we first have to confront an uncomfortable truth about ourselves. Modern treated lumber, the stuff we trust to hold up our decks, fences, barns, and porches, is fundamentally designed to fail. If you walk into any lumber yard today, you'll see neat stacks of green, pressure-treated pine, each board infused with chemicals like ACQ or micronized copper azole. The theory is simple. Pump biocides deep into the wood so fungi and insects die before they can feast. And on paper, it sounds effective. For a few years it even is. But beneath that thin veneer of modern engineering lies a fatal flaw. Our entire preservation strategy rests on one philosophy: the sealed envelope. We coat, spray, pressure inject, and paint wood as if wrapping it in plastic will somehow protect it from the universe. Yet wood is alive, or at least it behaves like something that remembers life. It swells when humidity rises, contracts when the air dries, and moves with every season. This is where physics betrays us. Wood expands and contracts at a completely different rate than the synthetic coatings we smother it with. As the wood swells, the rigid acrylics, polyurethanes, and pressure treatment films simply cannot flex enough to follow. So they crack, not visibly at first, but microscopically. Those microscopic fractures are all the invitation water needs. Once moisture enters, the tragedy begins. The coating that was meant to protect now traps the water inside. Since the barrier is impermeable, the moisture cannot escape. The wood's internal humidity rises above the critical 20% threshold, the point at which fungal life ignites like a biological switch. Soft rot fungi, anaerobic bacteria, and decay organisms quietly begin their work from within. From the outside, your fence still looks solid. Touch it with a screwdriver, though, and it collapses into powder. The rot didn't arrive from the surface, it grew from the prison of moisture we accidentally engineered. This is the failure of the film-forming mindset, the idea that wood should be sealed off from nature instead of allowed to live within it. The ancients never made this mistake. They didn't have plastic, so they never tried to suffocate the wood under a synthetic shell. Instead, they observed wood as a breathing material, porous, dynamic, thirsty, and worked with those characteristics rather than against them. Their preservation didn't trap moisture. It repelled decay while letting the timber exhale, expand, and contract in harmony with the climate. And that is why their structures endure for centuries, while ours struggle to survive a single mortgage cycle. Part 2. The Divine Resin, the Science of Pine Tar. To unlock the secret of why ancient wood endures for centuries, we must begin with a substance so revered, so foundational, that even Pliny the Elder wrote about it nearly 2,000 years ago. A substance so essential to the Viking world that archaeologists now believe its mass production wasn't just a craft, it was an industry powerful enough to fuel Norse expansion across oceans. That substance is pine tar, and not the diluted pharmaceutical kind you might see in a modern shop, but true Stockholm tar, born from the destructive distillation of resin-rich pine roots. This was chemistry long before anyone used that word. Now this is where the story becomes almost alchemical. When pine roots are burned in a low-oxygen environment, a process known as pyrolysis, you don't simply melt sap, you crack open the lignin and hemicellulose that form the wood's internal skeleton. What drips from that kiln is not a single compound, but a molecular symphony containing thousands of components. Among them, two families dominate: resin acids such as abiotic acid, and the real warriors of this mixture, phenols. Phenols are the key to understanding the genius of pine tar. In nature, these molecules form part of the tree's immune system. They are antiseptic, antimicrobial, antifungal, nature's own chemical weapons. When the Vikings coated their longships in pine tar, they weren't just waterproofing them. They were arming the hull with the concentrated immune system of the forest itself. But the brilliance doesn't stop at its chemistry. Unlike modern paint, which sits on the surface like a brittle shell, pine tar is built to infiltrate. Its aromatic hydrocarbons and terpenes are small enough to migrate deep into the timber. And when heated, they dive even deeper, slipping into the wood's tracheids and parenchyma cells, saturating the very architecture of the timber. Once inside, pine tar doesn't harden into something fragile. It cures slowly, remaining semi-fluid for years. That flexibility is everything. As the wood expands in humid summers, contracts in freezing winters, and breathes through every seasonal shift, the tar moves with it. It bends, it adjusts, it survives. And this wasn't a cottage industry convenience. Archaeologists in Sweden have uncovered enormous tar pits, industrial kilns dating back to the 8th century, capable of producing up to 80 gallons of pine tar in one burn. A single Viking longship needed roughly 130 gallons to seal its hull and even treat its wool sails. Without this industrial-scale chemistry, the Viking Age as we know it would never have unfolded. Their ships would have rotted long before touching the shores of England, France, or the rivers of Eastern Europe. Yet even this miracle substance had limitations. Pine tar alone is sticky, painfully slow to dry, and under extreme cold it can become brittle. It needed a partner, a binder that could deepen penetration, stabilize the coating, and transform the tar from a brilliant idea into a legendary preservation system. And that next ingredient would change everything. Part 3. The binder. The role of linseed oil. Now that we have uncovered the divine resin that protected Viking ships across brutal seas, we turn to the second ingredient in this ancient trinity. It is quieter, subtler, and far more scientific than it first appears. Yet without it, pine tar would never have become the legendary preservative it is. Enter boiled linseed oil. Pressed from the seeds of the humble flax plant, linseed oil is unlike ordinary oils. It belongs to a rare class known as drying oils, though the name is misleading. It doesn't dry by evaporation, the way water disappears from a puddle. Instead, it dries through a slow, powerful chemical reaction with oxygen, known as polymerization. This reaction is the secret to its strength. The oil's fatty acids, especially linolenic acid, link themselves to oxygen molecules. As they bind, they form a flexible, durable, polymer-like network that clings to the fibers of the wood. It is not a film on the surface, it is a transformation within the grain. And here is where the brilliance of the ancients truly shines. When linseed oil is mixed with pine tar, it creates something more than a blend. It becomes a vehicle. The oil thins the thick, resinous tar just enough to let it seep deeper, far deeper, into the microscopic pathways of the timber. Then, once the mixture has penetrated, the oil begins its slow polymerization. It locks the antiseptic phenols and resin acids inside the wood, creating a flexible, breathing armor. The wood stays supple, it resists cracking, it moves with the seasons instead of splitting under their pressure. And in doing so, it denies water the tiny fractures it needs to invade and feed rot. For centuries, sailors understood this intuitively. They mixed pine tar, linseed oil, and turpentine into a thick, fragrant brew they called boat soup. It wasn't a fancy brand name, it was a lifeline. Every hull, mast, oar, and railing that crossed cold northern seas was baptized in this mixture, and the ships that survived longest were almost always the ones coated by hand with this ancient science. But if the story ended here, we would only have two ingredients. The ancients, however, were masters of observation. They knew there was still one missing piece, an ingredient most modern woodworkers never think about. It was the key to creating a chemical environment where fungi, bacteria, and decay simply could not live. And that secret ingredient is coming next. Part 4. The Lost Variable. The Power of Hardwood Ash. Now we arrive at the ingredient almost everyone overlooks, the one hiding in plain sight for nearly 1,000 years. If you study the old stave churches of Norway, or examine the residue scraped from their ancient beams, you will find chemical fingerprints that should not appear in a simple mixture of tar and oil. You find calcium, you find potassium, you find silicates. In other words, you find ash, specifically fine, sifted hardwood ash taken straight from the craftsman's hearth. At first glance, adding ash to a premium wood preservative seems absurd. Why contaminate a carefully prepared mixture with what looks like dirt? But this wasn't a shortcut or a cheap filler. This was precision chemistry, centuries before the word chemistry entered everyday language. To understand the brilliance of this choice, we must look at the biology of rot itself. Wood decay is driven by fungi, organisms like brown rot and white rot, masters at breaking down cellulose and lignin into spongy ruins. These fungi thrive in mildly acidic environments, usually somewhere between a pH of 4.5 and 6.0. Within that narrow range, they release enzymes that tear apart the wood's structural fibers. Hardwood ash, however, is a completely different world. It is composed largely of calcium carbonate and potassium hydroxide, materials with a pH soaring between 10 and 12. This is the same chemistry used to produce lye for soap making. When you mix this alkaline powder into the tar and oil, you dramatically shift the pH of the wood's surface. For a fungal spore landing on this treated timber, it's like stepping onto the surface of Venus. The environment is simply uninhabitable. The high alkalinity denatures the enzymes fungi rely on to digest wood. In effect, the ash creates a chemical firewall that rot cannot breach. Yet that is only the beginning. Hardwood ash provides two more critical advantages. First, UV protection. Sunlight is one of wood's most relentless enemies. Ultraviolet radiation destroys lignin, the glue that holds wood fibers together, causing surfaces to turn grey, brittle, and weak. The fine particulate matter in the ash works like a natural sunblock. It forms a pigment layer that absorbs and reflects UV rays, shielding both the tar and the wood beneath it. Second, pore filling. Wood is a porous material filled with microscopic channels. Ash particles act like tiny aggregates that thicken the mixture, filling surface pores, hairline cracks, and micro crevices. This reduces water infiltration and makes it much harder for boring insects to gain a foothold. When you put everything together, the so-called sludge becomes a beautifully engineered preservation system. Pine tar provides antimicrobial and insecticidal chemistry. Linseed oil delivers deep penetration and flexible binding. And hardwood ash contributes alkalinity, UV resistance, and structural reinforcement. This wasn't guesswork. It wasn't luck. It was the combined observational intelligence of countless generations who learned how to turn nature's raw ingredients into a defense system so powerful that medieval wood still stands today. And the final steps, how they applied this mixture, are even more revealing. Part 5. The ritual of application, heat and thirst. Knowing the ingredients is only half the battle. You could mix pine tar, linseed oil, and hardwood ash in a bucket, cold and sticky, and smear it over a fence post, but it would fail. The ancients understood something we often forget. Chemistry means nothing without thermodynamics. For this preservation system to work, two conditions must be met. The wood must be thirsty, and the mixture must be hot. Historical records from Scandinavia, along with modern conservation notes on stave churches, all repeat the same principle. Application happened in the warm months, never in the cold. And the mixture itself was heated, usually to around 60 degrees Celsius, or 140 Fahrenheit. The reason is simple but profound. Viscosity. At room temperature, pine tar behaves like cold molasses. It clings to the surface, reluctant to move, resisting penetration. But once heated, its intermolecular bonds loosen, and its thickness collapses into a liquid almost as thin as water. Suddenly, tar isn't a coating. It's a flowing river of resin acids and phenols, ready to infiltrate the wood. When this hot mixture meets dry, warm timber, something remarkable happens. Capillary action ignites instantly. The wood doesn't just absorb the preservative, it drinks it. And not by a few superficial millimeters like modern deck sealants. The saturation can reach centimeters deep, driving into the grain, the fibers, and most critically, the end grain. The Vikings and medieval builders were almost obsessive about the end grain. To them, wood was not a block. It was a bundle of straws. Paint the sides of the straws, and you protect very little. Leave the ends exposed, and they act like open pipes, sucking in water, mold, and decay. So they developed rituals of immersion. They heated long troughs of their tar-oil-ash mixture and lowered the ends of posts, beams, and planks into the liquid. They left them soaking for hours, sometimes an entire day, until the wood reached what craftsmen called a state of refusal, meaning it physically could not absorb one more drop. That moment marked the difference between painting and preservation. Painting is a cosmetic act. It is a film, a disguise, a temporary promise. Preservation, in contrast, is transformation. It reaches inside the material, altering its chemistry, its flexibility, its resistance to rot. In other words, medieval craftsmen weren't coating wood, they were changing what the wood was. And this ritual, forgotten by the industrial age, is the reason their structures still stand, while ours crumble in mere decades. Part 6. The evidence of resilience. To understand the power of this forgotten wood dip, we don't need theory. We only need to look at the proof. Proof that has been standing for more than 8 centuries beneath some of the harshest weather on Earth. The Borgen Stave Church in Norway was built around the year 1180. For over 800 years, it has faced relentless rain, brutal snowstorms, biting winds, and constant UV radiation. There is no pressure-treated lumber hiding inside those walls. No modern membranes. No Tyvek. No copper preservatives forced into the grain. Its armor is tar, a tar infused with oil, ash, charcoal, and time, reapplied by human hands generation after generation. And the results are astonishing. The north-facing walls, protected from direct sunlight, still hold much of the original timber, placed there in the 12th century. The south-facing walls, exposed to centuries of sun, show expected weathering, yet the structure stands strong. Nothing has collapsed, nothing has rotted beyond repair. When archaeologists examined the residue embedded in the church's exterior, they found traces of charcoal, ash, and mineral particulates mixed into the resin. These weren't contaminants, they were ingredients. They were the signature of the recipe itself, preserved as clearly as a handwritten instruction from a medieval craftsman. Now compare that to the fate of modern lumber. We are sold deck boards with 15-year guarantees that rarely survive half that time without peeling, cupping, splitting, or rotting. We are pushed to buy sealants that crack within 3 seasons, paints that blister in the sun, and preservatives that give up just when the warranty expires. It is not preservation, it is planned obsolescence. The ancient method, by contrast, was built on the philosophy of maintenance, not replacement. You don't scrape pine tar. You don't sand it down. There is no endless cycle of stripping and recoating. When the wood begins to look dry, after 5 years, 10 years, sometimes longer, you simply warm the mixture again and apply another coat. The new oil reactivates the old tar. The old tar welcomes the new, and together they sink deeper into the wood. This creates a cumulative protection, layer upon layer, decade after decade, that strengthens with age instead of diminishing. A board treated this way today will be better protected 10 years from now than the day you first applied it. This is why stave churches still stand. This is why Viking ships survived centuries underground. And this is why, if we revive this lost technology, your own structures could one day endure long enough to confuse archaeologists of the distant future. Part 7. How to reclaim this technology. Now that we understand the science, the history, and the astonishing resilience of this forgotten wood dip, the question becomes almost irresistible. How do we bring it back? How do we, in the 21st century, with all our modern tools, distractions, and disposables, reclaim a preservation method that outperforms billion-dollar chemical industries? The answer is far simpler than you might expect. You don't need a factory. You don't need a lab. You don't need permission. You need a fire and a pot. Because this ancient protective mixture, this boat soup that kept Viking ships alive in salt water, sun, and storms, is something you can make at home, with ingredients that still exist exactly as they did 1,000 years ago. The formula is elegant, almost poetic in its simplicity. You combine 1 part authentic pine tar, true kiln-burned tar, not coal tar, which is toxic and entirely different in chemistry. You then add 1 part boiled linseed oil, purified so it does not go rancid. After that, 1 part turpentine, serving as the solvent that helps the mixture dive deep into the wood grain. And finally, the forgotten variable, hardwood ash, sifted fine to remove grit, stirred in until the mixture thickens just enough to hold its body while remaining brushable. But knowing the ingredients is only the beginning. The method matters just as much. You heat the mixture carefully, aiming for around 60 degrees Celsius, 140 Fahrenheit. The easiest and safest way is a double boiler or an old crock pot, because an open flame near turpentine is a disaster waiting to happen. Heat transforms the viscosity, turning the tar from sticky molasses into a flowing river of resin and oil ready to penetrate. Then you turn your attention to the wood. It must be dry, truly dry, because water hiding in the grain will block absorption. Once the wood is prepared, you brush on the hot mixture, slowly, deliberately, letting the timber drink it in. And if you are treating posts that will go into the ground, you immerse the bottom portion and let it soak until the wood refuses to take more. After that, you wait. This is not modern acrylic paint that boasts a 1-hour quick dry. This is chemistry that takes its time. The mixture may remain tacky for days, even a week, as UV light and oxygen begin the slow process of polymerization. It is a finish that smells like campfire and pine forests, a scent that lingers, earthy and bold. For some, it is the smell of craftsmanship. For others, perhaps less so. Which is why this mixture belongs outdoors unless you want your entire home to smell like a Viking shipyard. And then there is one final warning. One every old carpenter knew by heart. Linseed oil generates heat as it dries. If you toss oily rags into a pile, they can ignite on their own. Lay them flat to dry or soak them in water. You are trying to preserve your fence, not accidentally burn down your garage. But if you follow this process, if you mix, heat, apply, and wait, you are not just coating lumber. You are resurrecting a preservation technology that predates modern chemistry, yet surpasses it in longevity. And the wood you treat today may very well outlast you, your children, and possibly the walls of the house that stands behind it. Conclusion: the philosophy of durability. As we come to the end of this journey, one question lingers in the air like the scent of warm pine tar. Why was this knowledge forgotten? The answer is simple but tragic. We traded longevity for convenience. We surrendered centuries of wisdom for the promise of maintenance-free materials that were never truly maintenance-free. We replaced the smell of forests and fire with the harsh sting of volatile industrial compounds. And in our obsession with speed, efficiency, and disposability, we allowed one of humanity's most resilient preservation technologies to slip quietly into obscurity. But the world is changing. Supply chains strain, lumber prices climb, and the illusion of a disposable society grows thinner every year. We can no longer afford to build things designed to rot. We can no longer rely on chemical shortcuts that peel, crack, and collapse long before their time. The survival of the stave churches, the preservation of Viking ships, and the endurance of ancient timber across Europe and Asia reveal a truth we desperately need to remember. Wood, when respected, when treated with the chemistry of nature rather than the chemistry of industry, can be an eternal material. It wasn't a miracle formula created in a lab. It was pine roots, flax seeds, and the ash of last night's fire. The ancients were not primitive, they were practical, they were observant. They understood that durability is not an engineering trick, it is a philosophy. It is the commitment to maintain, renew, and protect, rather than discard and replace. They built with an eye not toward the next decade, but toward the next century. And so the next time you begin a project, whether it's a fence, a shed, a garden bed, or a cabin, don't just paint it. Don't settle for coatings that trap moisture and accelerate decay. Instead, preserve it. Mix the potion, heat the oil, stir in the ash, and transform ordinary lumber into something that might one day bewilder archaeologists who dig it from the earth 1,000 years from now. This is Historia Prime. If you believe these forgotten skills deserve a place in our modern world, like this video, share it with someone who values craftsmanship, and help us keep these lost sciences alive. Until next time, keep the fire burning.